Student, we will discuss here one more MO diagram. As a student, you should able to construct the MO diagram for nitric oxide. You should fill the electron in various labeled molecular orbitals. You have to find bond order. You have to comment on magnetic property and stability of the molecule.
In nitric oxide, two atoms are there. One nitrogen and other oxygen. Who is more electronegative? Oxygen is more electronegative. So energetics of its orbitals will be lower compared to energies of orbitals of nitrogen. Let us start from their basic electronic configuration. Nitrogen, atomic number 7. So electronic configuration 1s2, 2s2, 2p3. And what about oxygen? Atomic number 8. Electronic configuration 1s2, 2s2, 2p4. About 1s orbitals, those are inner orbitals. So they will not be involved in the formation of molecular orbitals because third condition, appreciable overlap, that will not be fulfilled, though rest of the conditions can be fulfilled. Among those two 1s orbitals, which 1s orbital will be of lower energy? I consider three compartments. Atomic orbitals of nitrogen, molecular orbitals of nitric oxide, and atomic orbitals of oxygen. Now I am with two orbitals. 1s orbital of nitrogen and 1s orbital of oxygen. Which orbital will be of low energy? Yes, it is of oxygen. When I have to consider molecular orbitals, so it is a part and parcel of molecular orbital as a non-bonding orbital. I label it as 1 sigma. Why sigma? I told to you, along bonding axis, along the axis, principal axis, it has the phase similarity. Means by rotation, phase is not going to change. Same thing about other 1s orbital of nitrogen. So it's 1 sigma, is a 2 sigma. Now actual molecular orbitals will start from 2s orbitals. 2s orbital of nitrogen and 2s orbital of oxygen, they will interact to produce one bonding sigma orbital and anti-bonding sigma orbital. It is a third bonding orbital, third sigma orbital, 3 sigma, and it is a
4 sigma star.
And mixed sp diagram we are considering. So when 2p orbitals, 2p orbital of carbon and 2p orbitals of oxygen, when they will mix, result will be pi 2p y and pi 2p z. So it is a 1 pi set. 5 sigma. It is because of sigma 2px. Upwards. Pi star 2px and pi star 2py. It is second pi set. And last, it is a sigma star 2px orbital. It is our sixth sigma set. Sixth
sigma star orbital.
Now let us fulfill the electrons. In 2s and 2p orbitals of nitrogen, how many electrons are there? 5. In 2s and 2p orbitals of oxygen, how many electrons are there? 6. 5 and 6, 11. So let us distribute 11 electrons. 2 electrons in 3 sigma orbital. 2 electrons in
4 sigma star.
4 electrons in 1 pi orbital. 2 electrons in 5 sigma orbital. And 1 electron comes in
2 pi star
anti-bonding orbital. Let us find the bond order. Bond order for this molecule is equal to number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. How many electrons are there in bonding orbitals? 3 sigma, 2 electrons, 1 pi, 4 electrons, and 5 sigma, 2 electrons. So total number of electrons 8 in bonding orbitals minus how many electrons are there in anti-bonding orbitals?
4 sigma star,
2 electrons,
2 pi star,
1 electron. So 3 electrons are there in anti-bonding orbitals. 8 minus 3 divided by 2. 5 divided by 2. Answer is 2.5. Yes. 2.5 is a bond order. We were expecting 2, 3, 4. No, half bond order also impossible. Molecular orbital theory can properly explain that. 2.5 is a bond order for nitric oxide molecule. What about magnetic property? Paramagnetic or diamagnetic it will be? It is paramagnetic because of the presence of unpaired electron in
2 pi star set.
Additionally, Suppose if I ionize this nitric oxide, means if I remove the electron from antibonding orbital, suppose if I remove the electron from 2 pi
star,
then what will be the bond order? Just calculate. What is the answer? Bond order is 3. So nitrosonium ion, No plus, bond order increases, stability increases, bond length decreases, and this can be properly explained by molecular orbital theory. Some simple approach, general approach that we are discussing here.
Now let us have insight about combining atomic orbitals in detail. Symmetry of molecule matters more. It is a heteronuclear diatomic molecule. Point group is C infinity V. Possible operations are C infinity and the vertical planes, the important operations that I am saying, about which the atomic orbitals symmetry can vary. Here, nitrogen and oxygen, which have electrons in 1s, 2s and 2p, out of those 1s orbital that I am not considering, but last 4 orbitals, 2s and 2p orbitals from each atom, let us focus on those. Lowest possible energy here is of oxygen 2s orbital minus 32.3 electron volt, and highest energy is of nitrogen 2p orbital minus 13.2 electron volt. Energetic point of view, direct combination between 2s orbital of oxygen and 2p orbital of nitrogen may be not possible, but via media, via 2s orbital of nitrogen, nitrogen to 2p orbital of oxygen, 2p orbital of oxygen to 2p orbital of nitrogen, the sp mixing is possible. And molecular symmetry allows us to interact 2s and 2p orbitals because there is no horizontal plane and there is no center of inversion. So sp mixing will be there. Sp mixed MO diagram, you are aware about that. Bonding sigma to px orbital means we label it as 5 sigma orbital remains of higher energy than 1 pi set. I like to bring your attention to a white small font written thing. Ionization energy of nitric oxide is 9.3 electron volt. About atomic orbitals, highest energy is minus 13.2 electron volt, and energy for nitric oxide highest occupied orbital is minus 9.3 electron volt. So I can say HOMO, highly occupied molecular orbital, has energy minus 9.3 electron volt. What do you think? This energy minus 9.3 electron volt is higher than the 2p orbital of nitrogen or lower? It is higher. Let us see molecular orbital diagram. See here, 3 compartments are there. Left compartment, atomic orbitals of nitrogen. Middle one, molecular orbitals of nitric oxide. And right side, atomic orbitals of oxygen. And pay attention towards left side arrow. It's an energy arrow. 1s orbitals from nitrogen and oxygen are there. But since they are remaining non-bonding, and in order to emphasize more on the 2s and 2p, I am not representing them in this MO diagram, but they are part and parcel of the molecule. Let us come to the 2s orbital of nitrogen and oxygen. Being oxygen more electronegative, 2s orbital of oxygen is near to the nucleus compared to 2s orbital of nitrogen, causing energy of 2s orbital of oxygen is lower. As per the basis of molecular orbital theory, if two atomic orbitals are combining, two molecular orbitals will be there. And here two molecular orbitals are 3 sigma and 4 sigma star. One is bonding, one is anti-bonding. One can help for bonding, one can oppose for the bonding. So net result will be no contribution forward the bonding. Come to the higher orbital, 2p orbital of nitrogen and 2p orbital of the oxygen. Here, because of sp mixing, sigma to px orbital Means we say here as 5 sigma orbital is of higher energy than 1 pi set of orbitals. About antibonding orbitals, as usual, pi bonding orbitals are of low energy, pi antibonding orbitals, and sigma antibonding orbital is of high energy. Total number of electrons, if you count, 3 electrons are there at nitrogen and 4 at oxygen. So 7 electrons, how can I distribute? 4 electrons will enter in the 1 pi orbital and 2 electrons in 5 sigma orbital, and remaining 1 electron is at 2 pi star orbital. Interesting. Do you remember I have asked the question, what will be the energy of HOMO of the molecule compared to 2p orbital of nitrogen? It will be larger, it will be higher. Yes, outermost electron, last electron is entering in antibonding orbital. Therefore, HOMO has higher energy than highest occupied atomic orbital, that was 2p orbital of nitrogen. So what do you think, that outermost electron is easy to remove? Yes, since it is in antibonding orbitals and electron in antibonding orbitals opposes the bonding, it is easy to remove. Suppose if I remove the electron, then what do you think, bond strength will increase or decrease? We will discuss that when I'll come to the bond order of the nitric oxide. I'll discuss the bond order for NO plus ion also, who is more stable, that we can discuss. So is this MO diagram for nitric oxide clear to you? See the electronic configuration of nitric oxide molecule. 1 sigma orbital is a non-bonding orbital and it is due to 1s orbital of oxygen. 2 sigma orbital also is non-bonding orbital and it is due to 1s orbital of nitrogen. Both have 2 electrons which are not responsible for any bonding or anti-bonding. Actual bonding anti-bonding chemistry start from 3 sigma. 3 sigma is a first bonding orbital which has 2 electrons. 4 sigma star, first antibonding orbital, has 2 electrons. Then 1 pi set, bonding orbital, 4 electrons. 5 sigma bonding orbital, 2 electrons. 2 pi star set, antibonding orbitals, 1 electron. And 6 sigma star, no electrons. So if you see these orbitals, 2 are non-bonding orbitals, those are represented at the beginning. Afterwards, 3 are bonding and 3 are anti-bonding molecular orbitals. What is the formula to find the bond order? Number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. Now which bonding orbitals are here? 3 sigma, 1 pi, 5 sigma. How many electrons are there in those orbitals? 8. Which are antibonding orbitals? 4 sigma star, 2 pi star and 6 sigma star. Total how many electrons are there in those antibonding orbitals? 3. So my answer for bond order can be 8 minus 3 divided by 2 is equal to 2.5. 2.5 is a bond order for nitric oxide molecule. And practically also we found the same is as a case. Now I said you, we will discuss about the removal of electron present in the antibonding orbital. Let us consider. I removed the electron from 2 pi star orbital. So electron from antibonding orbitals will decrease. Bond order will increase or decrease? Yes, bond order will increase. What will be the bond order? Bond order will be 3. And that NO plus will be stable. stable because of higher number of bonds. One may be with the question, but there is a charge. So if charge remains to 1 where, then molecule or ion, how can it be stable? Yes, question is absolutely right. But see, nitric oxide, nitrogen and oxygen, they have relatively same electronegativity. And because of same electronegativity, if any charge remains, that will be distributed among those nearly equally. Because of distribution of the charge, problem of charge will not come. If electronegativity difference would have been the more, the ion will be what, the less stable. But since electronegativities of nitrogen and oxygen are nearly same, NO plus despite of positive charge is more stable and bond order on other hand is increasing. Now see magnetic property. Is there any unpaired electron in molecular orbitals of nitric oxide? Yes, because of that unpaired electron, it is paramagnetic in nature. What do you think? NO plus will be paramagnetic or diamagnetic? It will be diamagnetic. Okay, students, now it is a time to know the homework. Three questions are asked here. The first one, in my presentation, I mentioned one where ionization energy of nitric oxide. What is the value of that ionization energy? And as per the information of the ionization energy, just use your common sense and find the energy of outermost orbital in the molecule, means HOMO. What do you think? That energy of HOMO is higher than the 2p orbital of nitrogen or lower? That is the second question. And last question, just I talk about the formation of NO plus, means ionization of NO. NO plus means nitrosyl or nitrosonium ion. Who is more stable, NO or NO plus? So these three questions, their answers, I expect them in comment box. I am waiting for your answers.